Welcome to Robotics Lecture 10. This is your Professor Atif Fareed Mohammed. Let's continue learning where we left off. We will be looking at manipulator mechanism design, basing the design on task requirements, kinematic configuration, redundant and closed chain structures, actuation schemes, position sensing, force sensing. I have also written a complete Python program and generated some results for you to watch at the end of this lecture. Manipulation mechanism design applications in various industries such as manufacturing and healthcare is one of the examples. Let's look into this in a little bit more depth. Manipulator mechanism design is a critical aspect of robotics that involves creating systems capable of performing precise and controlled movements to interact with their environment. This process encompasses the selection and arrangement of mechanical components such as joints, links, and actuators to achieve desired motion and functionality. The tasks or the importance of tasks requirements. The key considerations in the design include the kinematic configuration, which determines the range and type of motion possible, as well as integration of sensing and actuation schemes to enable accurate positioning and force control. Identifying task specifications, speed and precision requirements, environmental considerations, and constraints. Designers must account for factors such as payload capacity, speed, precision, and environmental constraints to ensure that the manipulator can effectively carry out its intended tasks. By carefully balancing these elements, manipulator mechanism design aims to produce robust and versatile robotic systems suitable for a wide range of applications, from industrial automation to medical procedures. The basics of kinematic configuration, the types of joints and links in manipulators, degrees of freedom and their significance. Let's look into this with an example. Kinematic configuration is fundamental to the design and functionality of robotic manipulators as it defines the structure and motion capabilities of the robot. Essentially, kinematic configuration refers to the arrangement of a robot's mechanical components, including joints and links, which determine how the robot can move within its environment. This configuration is crucial because it directly influences the robot's range of motion, precision, and tasks. Obviously, types of tasks it can perform. By carefully designing the kinematic configuration, engineers can create robots that are optimized for specific applications, whether it is assembly tasks in manufacturing, surgical procedures in healthcare, or exploration in hazardous environment. In robotic manipulators, joints and links are primary building blocks that define the kinematic configuration. Joints are the movable components that enable relative motion between adjacent links, and they can be classified into several types, including revolute or rotational and prismatic linear joints. Revolute joints allow rotational movements around an axis similar to a hinge, while prismatic joints permit linear motion along an axis like a slider. Links, on the other hand, are the rigid components that cannot actually perform separately, rather connect these joints, forming the structure of the manipulator. The combination of different types of joints and links result in various kinematic chains, such as serial and parallel configurations, each offering distinct advantages in terms of motion range, load capacity, and the precision. Degrees of freedom, or DOF, are a critical concept in kinematic configurations as they define the number of independent movements a robotic manipulator can perform. Each degree of freedom corresponds to a specific type of motion, such as rotation or translation along an axis. The significance of DOF, or degrees of freedom, lies in their direct impact on the robot's capability to navigate and interact with its surroundings. For instance, a robotic arm with 6 degrees of freedom can position and orient its end effector arbitrarily within its workspace, making it highly versatile for complex tasks. Understanding and optimizing the degrees of freedom in a robotic system is essential for achieving the desired balance between flexibility and control, enabling the robot to perform its intended functions effectively and efficiently. Serial versus parallel kinematic chains, the comparative analysis and application scenarios. Let's look into one such scenario. Let's look into industrial robotic arms used for assembly and manufacturing tasks. First, we discuss serial kinematic chains. These are commonly found in traditional industrial robotic arms, such as those used in automotive assembly lines. A characteristic features of serial manipulator in their sequential arrangement of joints and links, where each link is connected in series and the end effector is located at the end of the chain. The configuration allows for a large workspace and high flexibility, as each joint contributes to the overall range of motion. Serial manipulators are particularly advantageous in applications requiring a wide reach and complex motion paths, such as painting, welding, and assembly tasks. Their ability to maneuver around obstacles and access tight spaces make them heavily versatile. However, serial manipulators can suffer from lower stiffness and reduced accuracy due to the cumulative effect of errors and deflection along the chain. Whereas parallel kinematic chains, on the other hand, are exemplified by delta robots, which are often used in a high-speed pick-and-place operations such as packaging and sorting tasks. In parallel manipulators, multiple kinematic chains work simultaneously to control the position and orientation of a single end effector. The configuration provides several advantages, including high stiffness, precision, and the ability to handle heavier loads relative to their size. The parallel arrangement of links and joints allows for the distribution of forces across multiple paths, resulting in improved accuracy and repeatability. Parallel manipulators can achieve high speed and acceleration, making them ideal for tasks that require rapid movements. However, their workspace is typically more limited compared to serial manipulators, and their mechanical complexity can make them more challenging. In a comparative analysis, the choice between serial and parallel kinematic chains depends on the specific requirements of the application. Redundant structures in manipulators enhance flexibility and dexterity. The examples of redundant manipulators in real-world applications. Let's look into one scenario on this topic. An example of such a redundant manipulator is seen in the use of 7 degree of freedom robotic arm, which can mimic the capabilities of a human arm more closely than traditional 6 degrees of freedom robots. This additional degree of freedom allows the robot to adapt to various orientations and positions, making it highly versatile for tasks that require intricate movements. In real-world applications, these redundant manipulators are also utilized in medical surgery robots, where precision and adaptability are crucial for navigating the complex and delicate environment of human body. Closed chain structures. Let's look into this with a scenario. In an advanced manufacturing facility, a robotic system utilizing closed chain structures is deployed to enhance precision and rigidity in assembly operations. Closed chain structures, characterized by loops where the end of the kinematic chain is connected back to the base, provide significant advantages in terms of structural stability and accuracy. This configuration is particularly beneficial in tasks requiring high repeatability and load bearing capacity, such as the precise placement of heavy components in automotive assembly lines. The robotic system in this facility features the Stewart platform, a classical example of a closed chain mechanism which is used for fine tuning and alignment of engine parts. The platform's 6 actuators work in unison to provide 6 degrees of freedom, permitting for precise control over the position and orientation of the engine block. This level of control is crucial for ensuring that each component is placed with micron level accuracy, significantly reducing errors and improving the overall quality of the assembly process. The inherent rigidity of closed chain structures minimizes vibrations and deflections, which is essential for maintaining precision during high speed operations. This rigidity allows the robotic system to handle heavier payloads without compromising accuracy, making it ideal for tasks that require both strength and finesse. In addition to automotive applications, such closed chain robotic systems are also employed in aerospace manufacturing, where they assist in the assembly of aircraft components, ensuring that each part meets stringent quality standards. The use of closed chain structures in this manufacturing facility not only enhances the precision and efficiency of the assembly process, but also contributes to the overall robustness and reliability of the production line. By leveraging the unique advantages of closed chain mechanisms, the facility is able to achieve higher levels of productivity and quality, ultimately leading to improved performance and customer satisfaction. The types of actuators are electric, hydraulic, and pneumatic. The criteria for selecting appropriate actuation schemes, you will look into this with a real example that I have coded in Google Schoolab and shared with you in the last few slides, and you will be able to witness how these actuation schemes actually work. The position sensing introduction. Here, encoders, potentiometers, and resolvers are the main position sensors. A role in feedback control and accuracy enhancement. I would strongly suggest you to look into these topics at Google Scholar or IEEE Score to enhance your knowledge on encoders, potentiometers, and resolvers. That will give you first-hand experience and exposure to see what other researchers have conducted in their research work. Encoders in position sensing. The type of encoders are incremental and absolute. Working principles and advantages of encoders, we'll discuss that with a scenario and application in precise position measurement. We also look at that in one scenario. In the state-of-the-art robotics library, technically a laboratory is for Python coding, and laboratory where you actually work with the robots. Engineers are developing a robotic arm designed for high precision tasks such as microsurgery and intricate assembly operations. Central to achieving the necessary precision is the use of encoders in position sensing, which provide accurate feedback on the position of the robotic arm's joints. So this is a living scenario of a real laboratory with a Python library utilization. Encoders are essential devices that convert mechanical motions into electronic signals, enabling precise control and monitoring of the arm's movements. The laboratory employs two primary types of encoders, incremental and absolute, as discussed earlier, each offering distinct advantages depending on the specific requirements of the task at hand. Incremental encoders generate pulses as the shaft rotates, permitting the system to measure relative position change. These encoders are highly effective for applications which technically where changes in position rather than absolute position are critical. They are cost effective and provide high resolution, making them suitable for tasks requiring fine motion control. On the other hand, absolute encoders provide a unique digital code for each shaft position, offering the advantage of knowing the exact position immediately upon system startup without needing a reference or homing cycle. This capability is particularly valuable in applications where maintaining an accurate position is crucial even after power interruptions. The laboratory leverages absolute encoders in scenarios where the robotic arm must resume operations precisely from where it left off, ensuring continuity and accuracy in tasks such as surgical procedures. The applications of encoders in precise motion measurement are vast and varied within the laboratory. In the microsurgery setup, absolute encoders are used to ensure that robotic arm can make incision and manipulators, in reality the manipulations, with sub-millimeter accuracy, critical for patient safety and successful outcomes. Meanwhile, in the assembly line, incremental encoders assist in tasks requiring repetitive precision movements such as placing tiny electronic components onto circuit boards. By integrating these advanced position sensing technologies, the laboratory's robotic system achieve unparalleled levels of accuracy and reliability, pushing the boundaries of what is possible in both medical and manufacturing field at the same time. The potentiometers and resolvers, working principles and characteristics of potentiometers are suggested to look into Google Scholar and IEEE Explore. The working principles and characteristics of resolvers, do find those over there as well. Comparative analysis and suitable applications. This is where I suggest you seriously to look into Google Scholar, to look into these possible three scenarios and find out the research, what you get. And this will allow you to learn firsthand what other researchers have done. The importance of force sensing and robotic manipulators, we have discussed that in quite detail. These types of force sensors are strain gauges, load cells, and tactile sensors, enhancing manipulator interaction within the environment. We have looked into that in quite depth earlier, so I would skip this. I would suggest you to look into Google Scholar, how people have worked with strain gauges, load cells, and tactile sensors. This will allow you to know firsthand experience that these researchers have done in their traditional studies, and this will give you an exposure how several algorithms can be utilized at the same time in force sensing introduction in the laboratory scenario, as we discussed earlier, to exert certain force to do some tasks. The strain gauges and load cells, a little bit more explanation of working principles and benefits of strain gauges, characteristics and applications of load cells, integration in force feedback systems. Let's look into this with one scenario. Strain gauges are essential components in the field of mechanical and structural engineering, used to measure the strain or deformation of an object under various forces. These devices operate on the principle that electrical resistance changes when the conductive material is stretched or compressed, whereas load cells, on the other hand, are transducers that convert mechanical force into measurable electrical signals. and they often utilize strain gauges as a fundamental part of their design. A load cell typically consists of metal body to which strain gauges are bonded, arranged in a wheatstone bridge configuration to maximize sensitivity and compensate for temperature variations. When a load is applied to the cell, the resulting deformation causes a change in resistance of the strain gauges, which is then translated into an electrical signal proportional to the applied force. Load cells are crucial in various applications, including industrial weighing systems, material testing, and force measurements in robotic systems. Their ability to provide accurate and consistent force measurements makes them indispensable in field requiring precise control and monitoring of mechanical forces. Whereas strain gauges are widely appreciated for their precision, reliability, and ability to be integrated into complex systems for real-time monitoring and feedback. Let's look into one example of tactile sensors. In a cutting-edge robotics laboratory focused on developing advanced prosthetic limbs, tactile sensors play a crucial role in restoring a sense of touch to users. These sensors, designed to mimic the sensitivity and responsiveness of human skin, are integrated into the fingertips of prosthetic hands by using an array of pressure-sensitive materials and microelectromechanical systems, or MEMS. The tactile sensors can detect varying levels of force and texture, providing real-time feedback to the user. The technology enables individuals with prosthetic limbs to perform delicate tasks such as holding a glass without breaking it or feeling the texture of different fabrics, significantly enhancing their ability to interact with the world around them. The integration of tactile sensors not only improves the functionality of prosthetic limbs but also greatly enhance the quality of life for users by providing a more natural and intuitive experience. Integrating sensing and actuation, as we just discussed, the cutting edge solution using the tactile incorporation, amalgamation, to make sure that tactile sensors improving the functionality of prosthetic limbs, as we just discussed. These are some of the examples of integrating sensing and actuation in a robot or robotic movement. Let's look into a case study. Industrial robotic arm with task requirements and kinematic configurations, actuation, and sensing schemes employed, as I just mentioned. Medical robotic system, precision and safety considerations, as I discussed in quite depth. Use of advanced sensing and actuation techniques, as we just discussed. Actuation scheme comparison. This is the code which I wrote for a servo motor, which is a continuous control, and a stepper motor, which is a discrete control. You can look into both the blue and red in the servo motor, where input command occurs and servo response goes hand in hand in terms of positions or degrees, whereas stepper motor or discrete control is position in terms of desired position and actual position and how they compare with each other. The pneumatic actuator or fluid power can be looked into the pressure input and actuator response, whereas actuator performance comparison goes with speed as blue, precision is green, and force is red. And you can see servo motor, stepper motor, pneumatic, and hydraulic, how actuator type actually performed between 1 to 10 scale. These are the results of the code that I wrote in the Colab. The position sensing technologies, I wrote a code and I figured out the rotary encoder, which is digital, potentiometer, which is analog, Hall effect sensor, and LVDT, which is linear variable differential transformer. And these are all samples which I tried to portray here, so you can look into this and figure out that how actual Python code allows us to monitor and plot all these actions and tasks. The position sensing accuracy of encoder, potentiometer, Hall effect, LVDT, and capacitive is given on the left, and on the right the relative cost comparison is given between all these mentioned in terms of the relative cost that goes quite extensive when its capacitive kicks in. Force sensing technologies, a strain gauge force sensor, as I discussed in quite depth. The true force is blue and strain gauge input is red, and you can see the significance of actions of the force that can have using strain gauge force sensor. Whereas all these actions performed in a sample environment, which I had to write in quite depth, which I would suggest you try to mimic this and see if you can redesign this lab using these sensory inputs which are given on your screen at this moment. This will give you a hands-on writing experience of Python code for a robotic arm or a robotic movement. The frequency response, sensitivity, and maximum force range. This is a comparative analysis that I also conducted between strain gauge and all these load cells, etc. So you can look into this and see how these differentiators in terms of bandwidth, sensitivity, and maximum force occurs in reality. Integrated actuation and sensing systems, and these are the closed loop system response, actuator control signals, position error, and control system block diagram, which has feedback, set point, controller, sensors, and actuators associated. The real world examples, your car, the actuators are power steering, throttle, brakes, position sensors are steering wheel, position, pedal position. The force sensors are brake pedal, pressure, airbag, crash sensors. Your phone has actuators in terms of vibration motor, camera focus motor, whereas position sensors in your phone is accelerometer, nose orientation. Force sensors are pressure sensitive touch screen, and industrial robot has actuators in terms of motors for each joint. Position sensors are encoders on every joint, whereas force sensors are gripper force sensors to avoid crushing the objects. So the idea to learn in all this is in reality to figure out what are we doing and how we are manipulating our sensors in terms of robotics. Hopefully this lecture has given you something to learn. I would suggest you to conduct all the research using Google Scholar and or IEEE Explore or the university library to conduct more in-depth studies of the topics discussed in this lecture. Happy learning. See you in the next lecture.